Topic 8, Superposition. Part 2, Stationary waves or standing waves on the string. A stationary wave or a standing wave is formed as a result of two waves of the same frequency and same amplitude traveling in opposite directions along a string or in the air, and then superposition takes place. The two waves traveling in opposite directions arise because the incident wave gets reflected off the end of the string or the air pipe. Here is a detailed analysis of how two waves superpose to become a stationary wave. At the start, these two waves here, the solid one and the dotted one, are in phase. That means a trough meets a trough, a crest meets a crest, and they build up each other like this. Here's a resultant wave. At quarter period, they are completely out of phase. A crest meets a trough, a crest meets a trough, and they destroy each other. At half a period, they are in phase again. A crest meets a crest, a trough meets a trough, and they build up each other like this. At 3/4 period, they are out of phase, so they destroy each other. At full period, they are in phase again, they build up each other. Description of the previous diagram or previous slide. Each snapshot is taken at intervals of quarter period, where t is the period of the wave motions. The resultant wave does not move along the string. It is stationary or standing wave. This is interesting to note. The frequency of the stationary wave is the same as the frequency of the two individual progressive waves that interfere to make up the stationary wave. Here is a diagram of a stationary wave where there is no displacement, like this one here, this one here, this one here. They are called nodes. Where there is maximum displacement, like this one here, they are called antinodes. And two loops make up one wavelength. It makes sense because if you look at this wave here, starting from here, going down, up, down again, that's one wavelength. Or you could look at the other one, starting from here, up, down, up again, that's one wavelength. So here we have one wavelength. Standing waves on strings. If you clamp a string taut between two clamps and plug it, it will begin to oscillate. The one condition for these oscillations is that there must be a node at each end of the string. The string oscillates at its lowest and fundamental frequency, or sometimes called first harmonic, when it is plugged at the center, and it looks like this. There's a node here, there's a node there, here in the middle it oscillates, and it's antinode. A string that is taut will resonate with different frequencies. The lowest one is called a fundamental. When a guitar string is plugged, it will oscillate at the lowest frequency, this fundamental frequency. Then there is the second harmonic, third harmonic, and a fourth harmonic. And these are multiples of the lowest frequency. This is something you can try for yourself if you play guitar. It says here, if the string is plucked at a point a quarter of its length from one end, and then the string is lightly touched at its center, the first overtone or second harmonic will be seen or will be heard. By plucking and touching the string at different positions, different harmonics can be heard. So you can try it for yourself. Generally, in stringed musical instruments, the combination of the fundamental and other overtones or other harmonics determines the quality or timbre of the note produced. Here is an example you can try. It says here a stretched string of length 66 centimeters is plucked At its center, the stationary wave on the string is seen to have one antinode only. That means the fundamental frequency is displayed, and it oscillates at a frequency of 560 Hz, which is the fundamental frequency. Question A. Calculate the speed of the wave on the string. Question B. Determine the frequency of oscillation of the stationary wave when there are 3 antinodes on the string. Work out the answers yourself and compare yours with mine on the next slide. Here is question A. Divide the page into 2 halves. Here's question B. Question A is to do with fundamental frequencies, so the wavelength is equal to twice the length of string, and that is 1.32 meters. And the speed is equal to frequency times the wavelength. Frequency is 560 times the wavelength, which is 1.32, and it comes to 739 meter per second, 236 fix. That's the answer. Question B, that's dealing with third harmonic. So the length of the string is equal to 1.5 times the wavelength. So wavelength is the length of string divided by 1.5, which gives you 0.44 meters. And the frequency can be worked out by using this formula: speed over wavelength. Speed from question A is 739 divided by wavelength 0.44, and the answer is 1680 Hertz. These are just images of different stationary or standing waves that have been produced.